when we're looking at differential equations, one of the applications of differential equations is of what we call a logistics equation. And a logistics equation has a slightly different form. It's a differential expression that equals an expression here that has a constant times something in brackets, where we might have like a number 650, for instance, minus n. And so what happens is that if we take a look at this, it's really, you need some pretty advanced calculus skills to separate these variables and solve it for a general and a particular solution. So we typically don't try to separate these. In order to separate variables of this form, you actually need to have an advanced course called differential equations, which is a course you get to after calculus. And so we're looking then at really just kind of making some general conclusions about the general shape of what this looks like. And so this is one of two logistic equations that are real common, especially on the multiple choice portion of the AP exam. And so this form has, if we would solve this differential equation, be able to separate the variables and solve it, it has, if you notice, it has a logarithmic or a natural log or exponential sort of shape to it. And so really what we're concerned about is this basic shape, where we have this basic curve here, where we have an initial value, and then we have this this basic shape where it tends to be asymptotic about that value. And so we're just looking at some basic characteristics. Here's our initial condition. So here's our initial condition. And the asymptotic behavior here is what's really important. And that asymptotic behavior, if you might be able to kind of speculate on this, it looks pretty asymptotic to about this dashed line I'm trying to draw here. And you could probably guess what the value of this asymptotic or this asymptote is. And if we look back up here, it might just pop out at you here. This asymptote is at 650. So for this style differential equation, or this style logistics equation, this constant here happens to be the asymptote that we find when we graph this basic shape here. And of course, this curve then tends to flatten out. And if we talk about flattening out in terms of the derivative, that means that it is trending toward a differential value of 0. And knowing that, then we can then take this expression, and as you can see, if you solve that algebraically for the value n, divide each side by k, 0 divided by k is 0, you end up getting 650. And that's where that asymptote comes from setting the derivative equal to 0, no matter what the value of k is. The other type of differential equation is a differential equation that has a slightly different look to it. So it looks like this. And we still have, some parentheses here, but if you notice, we have the differential, the variable, that's part of the differential expression in 2 locations. Let me just flip back to the previous screen. Here we just had the variable y in the brackets, and this was a constant. So this other form, we have the variable both out here in front of the brackets and inside the brackets. And so this has if we notice, if we read the small print here, this has this is, we call this a first degree homogeneous function, because basically we can boil it down to it has one value of y, where this is a second degree homogeneous function, because we have y located in two locations. So this would be like a second degree. And so if we notice the shape takes on slightly different characteristics. It's more S-shaped, and that is the characteristic of that y being, if we would distribute into there, that y being squared, and we know that higher polynomials tend to cause things to bend, which is why we start to see this S shape. We still have this asymptotic behavior here. So we still have a situation where dy dt is going to trend toward a value of 0. But the neat thing is it trends toward a value of 0 as t goes to infinity. And also it trends toward a value of 0 at 0. So it's two locations. And that goes back to, if you remember, if we do distribute the ky into here, we get a quadratic expression, right? And so we're saying we're really solving a quadratic expression. And so you would expect to get two zeros when you solve a quadratic expression. So here it also the derivative trends to 0 at time t equals 0 as well. So we have that kind of dual behavior there. And so on these S-shaped curves, these second degree differential or logistic equations, second degree logistic equations, we have what we call this asymptotic behavior here, and we call that a lot of times the term carrying capacity will be used, and you probably can see that the term capacity is an appropriate term because we're talking about an upper value here. So there's the carrying capacity or that asymptotic behavior, and then we have the initial condition down here. So there's that initial condition at t equals 0. So this example here, this falls into that first degree homogeneous equation pattern. And so if we take a look at what this would look like graphically, we know the basic shape because we can see it's a first degree polynomial. So we know we have that that smooth curve, and we can start out with our initial condition. And so we know we have some asymptotic behavior here. And we'll figure out what that asymptotic value is. And so we know we have something that smoothly approaches that asymptotic behavior. Let me try to draw that a little better. That's about as good as I can get it. That smoothly approaches that asymptotic behavior. And so when we talk about the initial condition here, we say, well, we're talking about cows, and we're talking about cow's weight. And so what at the beginning, which would be when the cow was born, that would be the cow's initial condition, or the initial weight of the cow. And we're not too concerned about the value right now. We just see that in the problem here, that the cow weighs W sub 0 pounds at birth. So there's your initial condition. That's the intercept, so to speak. And we know that this this flattens out, so the derivative of this function is approaching 0 as time passes. And so we're just going to go ahead then and set the derivative of that function equal to 0. And once we do that, we can find the value of the weight that the cow approaches as the cow ages. And so as that cow ages, as we solve this, that cow is approaching 1,200 pounds. And so that asymptotic level is 1,200 pounds. If we take a look at this one isn't really too tough to solve. we actually can separate the variables without too much difficulty. We would have dw dt equals 1200 minus w, and we would have to take that entire expression 1200 minus w to the other side by dividing both sides by 1200 minus w. So I'm going to divide over here by 1200 minus w by writing it in fractional form. So we have dw over 1200 minus w equals, this is 1 dt. And as you can see, we're talking about now a situation where the variable is in the denominator. So we're talking a natural log integral here. So this would be the natural log of the absolute value of 1200 minus w. We have the chain rule here, so we have a minus sign out front, equals t plus a constant. And if we raise each one of these exponentially, then we can use our law of logs to go ahead and bring down this in front of the natural, or this in front of the exponential. Whoops. This in front of the exponential. And before I do that, what I really should have done is get that negative value on the right-hand side, and that helps us with the algebra a little bit. So we have 1200 minus w equals e to the minus t plus c, and so we have 1200 minus w equals, and using our laws of exponents here, we have e to the minus t times e to the minus c, but it is just a constant, and so a constant minus c, we could just call yet another constant. So we could call this a c1, and if I called that a c1, then we could really say that this is 1200 minus w e to the minus t times e to the c. And of course, e to the c, Euler's numbered to some power is just a constant. So we're just going to call that c e to the minus t equals 1200 minus w. And then we can go ahead and solve that for w and get the general equation, or the general form of this equation. And so, these aren't too bad to solve. That's a bit of a stretch for an AP Physics BC test, but not entirely ruled out. Here's an example of the second order differential equation. And so if we look at this, we can see that we have this power of 2 here. So we have this expression for the derivative that is quadratic in nature. So we're going to have those two situations where we're going to have a slope of 0 as we try to factor this quadratic expression. And so if we rewrite this in a form that might be a little more familiar, look a little more like the form that we had back here a few pages ago, we can factor out a constant, we can factor out one of the variables. So it looks like we can factor out 0.1p, and then we have a 1 minus something p, right? So if we factor out a 0.1 from here, that's like dividing by a 0.1. And so if we would divide by a 0.1, then we would take 0.0004, divide it by a 0.1, and we get 0.004. So this would be 0.004p. And so now it tends to look a little more like the the form that we had a little, just those 2 pages ago. And so if we would kind of get our basic shape here, and so what we're looking for in terms of these characteristics for this basic shape is that we're looking for the student being able to identify an initial condition, being able to identify a carrying capacity or an asymptotic line that is reached as time goes to infinity, and then being able to distinguish whether you do that basic curve for a first degree a homogeneous equation or that characteristic S shape for the second degree a homogeneous equation. And so we get this characteristic S shape, and then we're going to go ahead and just apply what we know about the derivative. The derivative out here is approaching 0, and the derivative right here is approaching 0. And so this really just ends up being really similar to an Algebra 2 question, is that we want to know what values of P make this equal to 0. And that's why I started to factor it here, because we're going to just say, well, we're either going to have one of two situations. We're going to have 0.1p equal to 0, or we're going to have 1 minus 0.004p equal to 0. And that's going to give us our two values along here for p. And so this one is a p of equal to 0. And this other one here, as we solve this, we'll take this to the other side. We've got 1 equals 0.004p, divide by 0.004, divide by 0.004, and so we have a value of p that is this divided by 0.004, and if we take 1 divided by 0.004, we get a value of 250. So we know that this asymptote is up here at 250, and that this initial condition is still kind of out there. We don't really have too much information about the initial condition, but we know that that we have a slope of 0 at this location as well.